Welcome to the deep dive.
Okay, so forget the bright lights, the really crowded center of our Milky Way for a bit. Today we're actually heading out the other way, towards the galactic anticenter, looking away from all that cosmic noise.
Mm.
And our mission really is to dig into what we're learning about our galaxy's shape, its history, um, from the discoveries being made out there.
Exactly. And we've got this amazing toolkit to help us, mainly data from the Gaia space mission, especially its early data release 3 building on DR2.
Gaia, right.
Think of it like having the best map maker ever, looking out our galactic back door, letting us see the bigger picture in a new way.
Perfect. So if you've ever looked up at the night sky, wondered about our spot in the Milky Way, well, this is for you. It's kind of a shortcut to some really exciting new astronomy. Okay, let's get into it.
Right, so first, just to set the scene.
Yeah.
The Milky Way. It's a giant spiral galaxy, basically a spinning island of stars, gas, dust.
Flat disk, mostly.
Yeah, a pretty flat disk where we live, rotating around a central bulge, and there's a bar structure in that bulge, too.
Then surrounding all that, there's the halo. It's more spherical, older stars, and the all-important dark matter.
And we're in the disk.
We are. About 8,000 parsecs out from the center. That's, what, 26,000 light years or so?
Yeah.
Definitely in the galactic suburbs.
Okay, so not right downtown. And the anti-center is just looking the other way.
Exactly.
Yeah.
Opposite the galactic heart. And the key thing is, instead of peering through all the dense star clouds and interstellar dust towards the center,
It's clearer out there.
much clearer. Fewer stars blocking the view, less dust. It lets us see much further out in that direction. Like looking at a city from the outskirts, not from, Times Square. You get a different perspective.
Makes sense.
And it's good to remember, our understanding of the Milky Way, it didn't just happen overnight. That bar in the center, only really confirmed in the 1960s.
Wow, that late.
Yeah, and the whole idea of the disk having a thin part and a thick part, that came about in the 80s. So even basic stuff is relatively new knowledge.
Which really sets the stage for Gaia, this game changer.
Oh, absolutely. It's hard to overstate the difference. Think about Hipparcos, a major mission before Gaia. It gave us great data for about 120,000 stars.
Which sounded like a lot then.
It was. But Gaia, we're talking about mapping nearly 2 billion stars. And not just nearby, but way, way out. The volume of space it covers is just vastly bigger.
It's like going from a local map to Google Earth, basically.
Pretty much. And it's not just where the stars are, it's how they're moving. Gaia measures their positions and velocities with incredible precision.
That's the key, isn't it? The velocities.
It really is. It lets us build, effectively, a 3D moving map of the galaxy, seeing how things are flowing, interacting. It's revolutionizing how we see the Milky Way structure and its dynamics.
So what are some of the big things Gaia's shown us, especially looking out towards this anti-center, like the disk itself? We knew it wasn't perfectly flat, right?
Right, the warp. That's been known for decades, like a vinyl record left out in the sun a bit, sort of bent up on one side, down on the other.
And we didn't know why.
Well, there were theories. Maybe the dark matter halo pulling on it, things like that. But Gaia DR2 data, looking at the velocities of 12 million giant stars, that gave us a new angle.
Okay.
Researchers like Poggio and his team found evidence suggesting it's not just a static bend, it's more like a ripple, an ongoing wave.
A ripple. Caused by what?
The likely culprit seems to be the Sagittarius Dwarf galaxy. It's a smaller galaxy orbiting us, and it looks like it's punched through our disk a few times in the past.
Ah, so disturbed the disk, and it's still sort of sloshing around.
That's the idea, like ripples spreading out on a pond after you throw a stone in. And Gaia DR2 also confirmed other waves, like a smaller up and down oscillation right here in our local bit of the disk.
So it's a pretty lively place, dynamically speaking.
Definitely not just smoothly spinning. And then there were these other features, ridges. Kawada and others found them in Gaia DR2 data back in 2018.
Ridges, what are those?
If you plotted the orbital speeds of stars, specifically their speed toward or away from us, between about 5 and 12 kiloparsecs out, you saw these diagonal patterns, ridges in the data.
Okay, so a warped disk, ripples, and velocity ridges. It's getting complicated out there.
It is. It tells us the disk is constantly being stirred up, influenced by things inside and outside. And the newer Gaia data, EDR3, let us see this even more clearly, especially towards the anti-center.
Sharper picture.
Much sharper. Antoja and her team used EDR3 to look way out, beyond 12,000 parsecs. They see even more complex velocity structures. There's an upward warping motion out there. Maybe linked to Sagittarius again, or maybe it's just how the disk formed, never quite settling flat.
And those ridges.
EDR3 confirmed the ones seen earlier extend out to maybe 14,000 parsecs.
Mm.
And interestingly, it revealed two more sets of ridges even further out, like 16 to 18,000 parsecs.
Wow. Still part of the disk.
Seems like it, yeah. They're still rotating with the disk. But why the velocities have this specific ridge structure? Well, that's still a big question. Something is organizing those motions.
Fascinating. Okay, let's shift focus slightly. What about the halo? The sphere of stars around the disk. Gaia's look there too, right?
Oh yes, big insights there. Using Gaia-DR2, astronomers looked at high-velocity stars near us, stars moving much faster or on different paths than typical disk stars. These are halo stars passing through our neighborhood.
And they plotted them on that diagram, the HR diagram.
The Hertzsprung-Russell diagram,
Yeah.
plotting brightness against color, basically.
Right.
And they saw two distinct groups among these fast-moving halo stars.
Two types of halo stars nearby?
That's what it looked like. And the theory put forward by Balbuzio and others in 2018 is pretty neat. They think the bluer group is actually debris from an ancient merger.
A merger. Like the Milky Way ate another galaxy.
Exactly, a fairly large one, apparently. They nicknamed it Gaia-Enceladus. So these blue stars are the leftover bits from that collision long ago.
And the other group, the redder ones.
They seem to be different. The idea is they were part of our Milky Way's thick disk that already existed before the merger happened. So the collision scattered some of them into the halo too.
So that one collision basically contributed a huge chunk of our halo.
Seems like it. It's a major piece of the puzzle of how our galaxy grew. And Gaia EDR3 lets us trace that Gaia-Enceladus debris even further out now, maybe 17,000 parsecs or more. It really reinforces the idea that a lot of the halo near us comes from that single event.
Incredible. It's like galactic archaeology.
Okay, going even further out now. Edge of the disk, anti-center direction. Are there structures out there too? Like clumps of stars?
There are. Even before Gaia, surveys like the Sloan Digital Sky Survey found hints of things. There's the Monoceros ring, for example.
Monoceros ring?
Yeah, discovered back in 2002, confirmed later. It's this large, sort of sheet-like structure of stars, about 10,000 parsecs from us, out towards the anticenter. It covers a huge patch of sky.
And there are others. Things called the anti-center stream, the Triangulum Andromeda overdensities. It looks like the very outer disk isn't smooth. It's got all this substructure.
And what are they? Leftover bits of eaten galaxies.
That was the first guess, naturally. Streams of stars pulled off dwarf galaxies. But the current thinking is leaning more towards them being part of the Milky Way's disk itself.
Oh, why the change?
Well, for one, we haven't found obvious parent galaxies they could have come from. But maybe more importantly, when we look at the stars in these structures, their chemistry, their ages, they look remarkably similar to regular thin and thick disk stars.
So they look like they belong to the Milky Way disk, just arranged strangely?
Pretty much like ripples or waves or just complex structures within the outer disk rather than something added from outside. The disk itself is just more complicated than we thought.
Okay. And you mentioned Gaia helps with star clusters too, open clusters.
Absolutely. Open clusters are groups of stars born together, so they're great for tracing the disk's structure and history. Gaia's data has been revolutionary for studying them, especially distant ones.
And there are some interesting ones out in the anti-center.
There are two really fascinating examples, Berkeley 29 and Saura 1. They're ancient open clusters, billions of years old.
Okay.
And they're way out there, about 20,000 parsecs from the galactic center in the anti-center direction. Plus, they're not even in the main plane of the disk. They're like 1,000 parsecs above it.
Whoa, so super far out and way off the beaten path. That sounds weird for disk objects.
Exactly. That was the big question. Given how far out and how high up they are, were they really part of the disk? Or maybe captured from somewhere else? The problem was measuring their movement accurately at that distance.
Too far away for good velocity data before?
Precisely. Tiny errors in how fast they seem to move across the sky, their proper motion become huge uncertainties in their actual space velocity and orbit when they're that distant.
But Gaia TDR3 changed that. Better measurements.
Much better. The improved astrometry, the precision in positions and motions from EDR3, plus being better able to tell which stars actually belong to the cluster, finally nailed it.
And the answer is?
Antosia and her team showed pretty definitively in 2021 that yes, Berkeley 29 and Saura 1 are moving on disk-like orbits. They are part of the galactic disk.
Okay, wow, so they belong. But that just makes their location even more puzzling, right? How did disk clusters end up way out there?
That's the million-dollar question now. Does the disk just extend much, much further than we thought? Or were they formed closer in and somehow got kicked outwards? Maybe through something called radial migration or interactions with Sagittarius or some other disturbance?
So these two old clusters are suddenly really important clues.
Vital clues. They're probes of the very edge of the disk telling us about its true size and maybe some pretty dramatic events in its past. It really underscores how much Gaia is pushing the boundaries.
It certainly sounds like it.
Yeah, as Antocha and her colleagues put it, Gaia EDR3, with its combination of precise positions, motions, and brightnesses, lets us extend the horizon for exploration towards the very end of the disk. We can now study these really old parts and see faint structures we couldn't resolve before. The impact is, well, it's huge.
Right. So wrapping this deep dive up, it feels like looking away from the bright lights towards the anti-center, especially with Gaia's eyes, has just opened up so much.
Absolutely.
We're seeing a disk that's not static, but warped, rippling, maybe from past collisions.
And a halo that seems largely built from at least one major merger.
Yeah, the Gaia-Enceladus event, and then this complex outer disk with
Yeah.
rings and streams and these ancient clusters hanging out in weird places.
It's forcing a rethink as how the Milky Way formed and evolved. The level of detail now is just incredible, revealing a much more dynamic history.
Which leaves us with a thought for you, our listener. If we're finding all this unexpected complexity, ripples, ridges, ancient relics, just by looking towards the relatively quieter anticenter, imagine what else might be hidden in the really dense, complicated regions closer to the galactic center.
Right. What other surprises are waiting in the Gaia data as we keep digging deeper? What will that tell us about our galaxy's whole life story, and maybe about how other galaxies like ours evolve too?
It really feels like we've just started a whole new chapter in exploring our own galaxy.
Definitely. It's an exciting time in galactic astronomy. The story is still unfolding, and there's always more to discover out there.
Absolutely. Keep looking up, keep wondering, and join us next time for another deep dive.